Well, we can go ahead and get started, Jonathan.
Okay. So I just commenced talking.
Absolutely. Well, I can introduce you. This is Jonathan Clarke, and his talk is Rising to the Challenge of Mars EVA Suits. Welcome, Jonathan.
Thank you, James. Welcome to my talk. It's a fine morning where I am, and hope you're having a good day wherever you are. So, rising to the challenge of Mars EVA suits is one of the all too often overlooked aspects of the challenge of going to Mars generally. So in this talk, I'll be introducing the challenge. I'll be looking at the requirements for Mars EVA suits, look at the issues of the current suits, and of course then wrap it up at the end. And some quotes to start with. The quotes that emphasize that when we're talking about Mars EVA suits, when we're designing them, we must focus on the end user. What does the astronaut on the surface want and need? Be they a scientist, be they an engineer, be they some other expertise. Because otherwise we design a suit that meets engineering goals, that meets the biomedical goals, but is pretty much useless. And certainly suits designed today, be they for the moon or for Earth orbit applications, have tended to be not particularly useful beyond the bare minimum for the users. And this is important because it is the differential between the performance of an astronaut, be it on the surface of the moon or the surface of Mars, and that of robotic missions, robotic technology that will provide the justification for humans on the surface. Here's a graph from a paper by Ian Crawford back in 2012. He looked at the productivity of lunar exploration, comparing the number of publications, the cumulative number of publications from robotic missions against those of the Apollo astronauts. And as you can see here, that the number of publications from the Apollo missions exceeded the results from the robotic missions by a factor of about 5 or 6. Furthermore, that the robotic missions generated data in the immediate mission period and after, but because the data sets were so small, the return eventually plateaued off, whereas data from the crewed missions continued to accrue, as it were, as people continued to work on the Apollo data, particularly the rock samples that were returned. And the greater we can increase the differential, the greater the likelihood that we will be able to get funding and useful results out of missions. And the key to that is an effective Mars EVA suit. So what are the requirements for Mars EVA suits? This is one of the most detailed work plans that have been developed, a straw work plan for time on the Martian surface for the NASA Design Reference Mission version 5 in 2009. An 18-month, 540-day mission, no more than 24 hours on EVA every week, up to 8 hours time spent on each EVAs, and 1 day off per week, and no more than 12 hours on consecutive days. And that is based on the performance of current suits. So the ideal Mars suit must be safe and comfortable for frequent use. If you're going out on the surface, pardon me, 3 days a week, you don't want it to be dangerous. You don't want it to be extremely uncomfortable. It's got to be light enough. It's got to be flexible and dexterous, and be able to maintain a comfortable environment within the suit, within the wider Martian context. And I'll be exploring all these, by the way, further on in my talk. And the other things like it's got to be worn for many times, several hundred times, unlike any previous suit. It's got to be rapidly replenished, easily serviced, easily cleaned. Not something that's often discussed, but if you're going to be wearing a suit for several hundred times on the Martian surface over an 18-month period, if you don't clean it, the outside is going to be pretty grotty, and the inside is going to be manky beyond all belief. So you'll need to be able to easily clean the suit with all of its complex instrumentation and technology. And here is sort of the supposed state of the art. The XEMU suit revealed with much fanfare in 2019 as a common design with variants for Earth orbit, the Moon and Mars. And the thing to note about it is that it's extremely heavy, over 183 kilos. For comparison, the Apollo lunar suits weighed less than 100 kilos. It's incredibly stiff because it's inflated to 56.5 kilopascals, about the same as a basketball. And you can imagine what it'd be like to sort of try and move arms and legs and fingers in something that stiff. It's cooled by sublimation, and you know, $400 million later, it still actually hasn't developed a fully operational spacesuit. It's still prototypes. So, given that, let's compare sort of the current state of the art with various issues. Safety comes first. And the reality is current suits, be they historic on the Moon or current suits in Earth orbit, are not only uncomfortable, but they injure the people wearing them. And there's a list of all sorts of things there. I won't go through all of them in detail, but physically, many astronauts have said doing an 8-hour EVA from the International Space Station is like running a marathon. And you can't run a marathon every other day like is expected for people to do on Mars, particularly people who are going to be in their 50s or 40s at best, potentially deconditioned after the journey. Note, though, the lunar surface. There are only 15 EVAs during the Apollo mission on the lunar surface, and there were 9 injuries. One, perhaps the most serious, was a deep wrist laceration where the cuff of the suit, which had a bearing, cut the astronaut's wrist to the bone. There was also a shoulder injury. Now that's unpleasant and not wanted, but you'd tolerate that when you're only doing 3 or 4 EVAs during a mission. Compare that with training exercises. 64% of astronaut trainees have had significant shoulder injuries, 9 requiring surgical treatment. That's not going to cut it on Mars, right? There are going to be no surgeries on Mars for the first few missions until we actually have a large permanent station. Even on large Antarctic stations today, we don't have the resources to do major shoulder surgery. And the biggest cause of these injuries is poorly fitting, stiff suits. And the main driver for the stiffness of a suit, a conventional gas pressure suit, is the inflation pressure. Apollo gloves, and Apollo suit in general, had 55.5 kilopascals. And these gloves had, according to the astronauts, only 10% of Earth normal effectiveness. Current suits are worse than that. The shuttle is almost 30 kilopascals, and the Orlan suit, the Russian Orlan suit, is 38 kilopascals. The direction of suit development since Apollo has been going the wrong way for pressurization. And the Apollo astronauts in vain said they would have preferred a lower pressure, 20, 21 kilopascals, as being the ideal pressure, at least for finger and glove dexterity. Another big issue is the load. I mean, it's all right in low Earth orbit where weight is 0 and mass is actually an advantage to some extent because there's more inertia and it stops you wandering off from your task. But on Mars, you'll need a lot smaller mass to haul around. And so work by Lunar and Wickman demonstrated that for sustainable effort, repeated EVAs on repeated days, the suit should mass no more than 50% of the body mass. Those numbers there are for the reference man and the reference woman. And the reality of people is they vary, so that's just an indication. So no more than 35 kilos for the entire Mars EVA suit imposes a severe limit on how we designed them. Remember, the Apollo suit massed just under 100 kilos, and the XEMU is 186 kilograms plus. Completely unwearable on Mars. For Mars, we'll need new thermal management. So as I mentioned, sublimation, basically subliming water into space on a cooling sublimator, is how every spacesuit since the late 60s has worked. Whether it's an Apollo suit or shuttle or ISS suit or the Russian Orlan, they all use sublimators. The problem is on Mars is that sublimation is not an effective cooling mechanism at pressures of above 4.7 hectopascals. There's an error in the slide there. And this pressure is actually at an altitude of 2,000 meters above datum on Mars. So something like 2/3 to 3/4 of the Martian surface, the pressure is too low for sublimators to be used. On top of that, sublimation coolers, because of all the water they haul around, are very heavy, about 60% of the Apollo suit, which when mass is such a constraint, is a really bad idea. One possibility is that we will use, we could use doffable and donnable layers, a bit like what we'd wear in cold weather. So if you're cold on the surface of Mars, you can put on this puffy jacket array like this prototype suit here, and as you work, you heat up, you can put that off. And there's been some modeling that shows that this will work on Mars, but no one has yet actually tried it for real in a low pressure chamber mimicking Martian conditions. And this brings us to a larger question, is that suits do not exist in vacuum. There's actually an entire ecological, technical ecosystem that they fit into. Things like habitat pressurization, airlock design, breathing gas mixtures. And one of the big issues for current EVAs is a huge amount of time needed to prepare for each EVA. Several days beforehand, then many hours, at least in the US suit, to pre-breathe, to remove nitrogen from your blood, and then about an hour to check out the suit itself. The Russian Orlan's a lot quicker because it works at a higher pressure, so less pre-breathe time, and there's a rear entry which allows people to slide into it and shut the hatch and off you go. So people have also been looking at the development of exploration atmospheres for the habitats on the Moon and Mars, called the exploration atmosphere, just over half of one atmosphere, 54.6 kilopascals, and oxygen enriched. And this is equivalent to an altitude of almost 5,000 meters with a higher O2 partial pressure. And I've worked quite a bit at those sort of altitudes. It doesn't take long to adjust. So there's me disporting myself on the Kardung Glacier in Ladakh at 5,600 meters, and a team from ESA who I was out there with are working quite happily on a prototype instrument for the Mars, for ExoMars lander at about 4,500 meters. So these are feasible pressures for working on Mars, and we need to think about people going from that into your Mars pressure suit, EVA suit, from that sort of environment. A bit more detail on what is expected for EVAs on Mars, repeating what was said earlier. Apollo, up to 4 EVAs in 3 days by 2 people. Shuttle, 5 EVAs. These are high intensity operations like fixing the Hubble or servicing the Hubble, ascending the ISS. Up to 5 EVAs in roughly 10 days, plus or minus a bit. On Mars, 540 days, 6-person crew, perhaps more, perhaps less. Many EVAs, shorter ones every day, longer ones every few days. 750 EVAs almost over that time. So we will need to adjust our expectations of EVA from infrequent operations to more frequent operations. And that means the suit concept must change in the words of my colleague, James Waldy, must move away from a personal spacecraft you get into to a garment that you just slip into and go outside. And one of the interesting things I've found is that if you look at the Apollo EVA record, although they stayed outside for hours, longest ones are about 8 hours, when you actually split the tasks they had to do, most of the tasks are actually quite short. And out of 53 task events, 48 of them out of 53 lasted for less than 2 hours. So again, we need to change our idea of a EVA suit from something that is you go out in with 8 hours resources on board, but rather something you go outside, do a short task, and then replenish before moving on to the next one. And this has an implication for our suit design overall. You know, rather than carrying consumables, you can plug it into a rover, refill the oxygen tanks, recharge the batteries, and move on. It also simplifies things like plumbing. And rather than doing whatever you have to do during the day in your suit, you follow your mother's advice and go before you go. So one solution to these very demanding challenges is MCP technology, mechanical counterpressure suits. These are tight, form-fitting suits that use elasticity to compress the body, to provide the necessary compression, not gas. It's been around for a long time. Fans of old science fiction movies would have seen things like the capstan suit here, which was developed as an emergency IVA suit for high altitude pilots in the 40s and 50s. And they provided short periods of mechanical counterpressure so the pilot could get down to a more hospitable altitude. The Webb activity suit, developed in the 60s and early 70s in the Apollo program, was a full body MCP suit. Very elastic fibers, and it was tested at Mars type pressures. And people could run wearing the suit, run normally in these suits. They could run upstairs, run up slopes, run down slopes, climb ladders, bend over, crouch, kneel, almost a full range of motion. And I apologize for the busyness of this table, but if we compare an ideal Mars suit and the requirements for it, we come to an overall score of about 42.5. Current gas pressure suits have a score of only 22 of meeting the necessary requirements. And MCP suits, as we currently envisage them, would have a score of 34.5. So in terms of the performance, in terms of the user, MCP technology seems to be extremely promising in meeting the requirements needed on Mars. Obviously, they're at a very low level of maturity, and there are many issues that need to be solved. What sort of material? Will it be woven fabric or knitted fabric, or a material, for want of a better word, like a wetsuit, a neoprene suit that hugs the body? Should it be segmented? Should you have a gas pressure torso and MCP arms and legs and feet and gloves and so on? Donning and doffing takes a heck of a long time, several hours for a full suit, for the Webb space activity suit. How durable are these materials? How do you distribute pressure with elastic materials over such a complex shape as a human body, particularly negative curvature spaces like the armpits and other parts of the body that I won't get into? How durable? They'll probably be passively cooled, as I mentioned, using puffy jackets. If it's a porous membrane suit, you can actually cool yourself by sweating through it. But that needs to be verified if you're going to trust your life to it. Waste management. You know, if you're only going out in this for a couple of hours, yeah, go before you go. But if you expect astronauts to wear it for 8 hours at a stretch, waste management becomes a problem. Yeah, might be a reason to use a gas pressure torso. And water loss. It appears from the notes of Webb and his colleagues that there's a lot of water lost through the skin in an MCP suit, possibly unsustainable. That needs to be investigated. Since Webb, there has been some work, mostly on gloves. James Wally, who's illustrated here, testing on contrasting a MCP glove funded by Honeywell with a conventional shuttle glove, developed a glove that had 3 layers. It could be donned in just a few minutes. worked at an Apollo equivalent pressurization. And it was, however, quite painful. I've worn it. I'm testing it out in the field at a normal pressure there in the bottom right. I wore that for several hours. It was almost a record, I think. And it was quite unpleasantly comfortable, although workable. But that only is the case when you're putting it on. When you put it into a vacuum chamber, suddenly that pressure disappears and it is very comfortable. And there's James, the bottom right again testing the field, in this case using a hammer. And you can see that it's very lightweight, unbelievable, very slim, and very flexible. The only full body suit done was in 2005 or 15 by a guy at University of North Dakota who developed this full body integrated suit that was tested in components in vacuum chambers, and its thermal balance was tested running on a treadmill. It has a hard torso which isn't pressurized, and it's basically for the life support system which was integrated with it, and for mounting the helmet. And the two designs were tested. A lot more work needs to be done, not on components, but on actually full body suits to address many of those larger integrated problems I mentioned. So at the end of further development, this might be the sort of suit that we'll see people working on Mars. Very snug fitting, extremely flexible. These are all proven aspects of it. A rigid shell for the torso, which serves as a mounting for a very slimline life support system, and in this case, an integrated helmet. And there he is, as all good astronauts do, collecting geological samples. The company that I'm contracting with, run by James Baldy, Human Aerospace, is also working on 3 other counter-pressure suits for use in the space environment that are relevant for Mars. They're looking at a zero-gravity countermeasure suit that longitudinally compresses the body to maintain bone density. This was developed in parallel, in partnership with MIT in the US and the European Space Agency. And there's Andreas Morgensen actually testing the suit on the International Space Station. It looks like he's wearing a t-shirt, but the suit itself is like a set of long johns. We're also working on an orthostatic intolerance garment. Astronauts, when they return from zero gravity, find their precious bodily fluids drain from their heads down to their legs, and this can cause fainting. And there's videos on YouTube about that. This compresses the lower body, a little bit like a pilot's G-suit, but does so with elastic fibers to prevent that happening. And the prototype of that will be delivered at the end of next year. And also a sensory motor skin suit to counterbalance the deconditioning people appear to experience in altered gravity. And again, that's going to be delivered by the contract by the end of next year. And both these countermeasure garments, all 3 of these countermeasure garments, are relevant to Mars for the journey to Mars or the immediate post-landing period. And the advantage is, unlike other suits, they're very compact. You can roll them up and stuff them in a backpack. They're extremely light and compact and quite comfortable. So in conclusion, I want to emphasize that Mars-specific suits are essential for the exploration of Mars. We can't just take existing suits, put a decent pair of boots on them, and then walk around on Mars. It needs a complete rethink in almost every aspect. Because current suits are inadequate. They're too heavy, they're too stiff, wrong thermal management, and they're extremely uncomfortable, in fact dangerous. Mechanical counterpressure is a promising way. It may not be the only way, it may not even be the way we choose, but I think it's a very promising way for us to investigate. But without the necessary revolution in suit design, humans will not be fully effective on the surface of Mars. Just the acknowledgement of many people who have helped in this and our funding source. And then it's over to feedback, your views.
Okay, yeah, so we have a few questions I can read to you. So the first question is there an exoskeleton that supports these suits?
No.
No. Okay.
And the closest thing that the average person might be able to experience is putting on a tight wetsuit.
Then Then does ILC Dover customize the suits, or are they generically sized?
Because of the need of high and even compression, these will be custom made for the astronaut. And in fact, the company, a spin-off company by James Bald, is actually doing this for athletic compression garments, which is quite a big thing. You know, you go in, you get laser scanned, and a thing is custom made for you.
Then is there a backup air straw mechanism in case the astronaut falls and cracks their face shield?
Well, the human skin is quite a good spacesuit. It supplies most of the pressure that you need. So if you cut your suit on a sharp rock or whatever, right, and you'll get a tear in it. And that local area may suffer some swelling, perhaps some capillary rupturing, a bit of bruising, but you won't die. Whereas you fall over in a gas pressure suit and rupture it, you will die quite quickly, you know, depending on the size of the hole. You might have a few minutes with a backup supply to get into it, whereas here, you know, all you have to do is head back to your pressurized environment, be it a vehicle or the habitat.
Then how do you see rescuers interfacing with the suits for rescues? And then lists a variety of different situations that can happen. Would you plan for attachment points, rigging systems, and first aid capabilities to be integrated into the suits?
If I understand the question, you're asking, can we have rigging for climbing or safety lines? Yes, you can wear a harness, a rigger's harness over the top of this without any problem.
Or like things that you can put onto the suit that would assist other people rescuing.
Oh, right, yeah. Well, remember, this is going to be much lighter than the other suit. You know, you're going to haul someone back into a pressurized environment. It'd be far easier if you and they are wearing one of these suits than a gas pressure suit. First aid, you're not going to do first aid in a gas pressure suit. If you tear an MCP suit, you may be something like duct tape. Wrap over the area with the tear might provide initial first aid, but the whole point is, just like an underwater accident, you are going to get them into a pressurized environment as quickly as possible. And again, this will be a much easier suit to get someone out to render first aid to an injury than a gas pressure suit.
And do you have any thoughts to share about mechanisms for ensuring that contaminants on Mars do not spread to the HABs or other interior environments, such as suit exterior scrubbers?
That's a good question. That's something that needs to be addressed. If you're using evaporative cooling, sweat cooling on Mars, obviously you want the suit to be permeable. In that case, and if you're really worried about contamination, I would envision an outer layer, a set of overalls that is fine enough to prevent forward and backward contamination, but at the same time, or minimize it, but at the same time can still breathe. That's a materials thing. I also think there is a lot of unnecessary caution in terms of forward and backward contamination. And recent reports have suggested that probably most of Mars, except special regions, which don't exist as far as we know at present, where life might exist, or even terrestrial life might be able to exist, most of Mars is probably no bigger an issue than the Moon. And you know, an outer suit like that would be would simplify things like cleaning the suit between EVAs, if they get too dirty. A Martian regolith is very different to my fine regolith is very different to that on the Moon. It's not as sticky, it's not as jagged, and it seems to sort of come off things very easy from what we've seen on the lander missions.
Okay, so we're now at the top of the hour, so other workshops are beginning, but Jonathan, if you'd like, we could continue with some questions, and people could leave to go to other workshops if they want.
Right. Okay. So they're in other chambers, so I can just stay here for this one.
Yeah. We can stay here answering questions if you like.
I'd love to.
Okay, so another question now is, what do you mean by sublimation in the suit?
You're all familiar with the fact that when water is warm, it evaporates. That's how our body cools. We sweat, that evaporates in the atmosphere. At low pressures, liquid water doesn't evaporate. Water doesn't go through a liquid phase. It freezes and then goes straight from solid to vapor. So current spacesuits from all countries use sublimation with water that's picked up heat from the body, goes through a sublimation plate where it's exposed to space, it freezes and then sublimates. And this is a very efficient way of rejecting heat or eliminating heat from the body. The space shuttle also used sublimation cooling for the whole spacecraft. Hope that makes sense.
Yeah, then how is sweat handled in the spacesuit? Also bacteria such as foot fungus causing agents?
If we're worried about terrestrial bacteria going onto the surface of Mars, which is a highly hostile environment for bacteria of all sorts, for the most part, we can wear an outer suit which can still transpire moisture as required water vapor, but the pores are small enough to minimize transfer of bacteria. But again, we won't worry about this on the moon, and I suspect from what we know about Mars, this is not going to be an issue on Mars.
And then question, are you familiar with the work of Professor David Newman at MIT about mechanical pressure suits?
Yes, I mean, my co-author James Baldy did his a postdoc with David Newman, and she was involved with the early development of the zero-G countermeasure suit. Yes, she's a person that human aerospace interact with regularly, and her team.
Okay, so we have a question now from the AltSpace VR. And so AltSpace VR, you can go now with the question.
I didn't hear anything.
Let's see, I think I...
Are you hearing me okay?
Oh, I can hear you now.
Oh, it's coming through? Okay, good. Yeah, I was just curious, are there any hybrids of maybe the mechanical variety of suit that would perhaps flow water or some other fluid or gas within pressurized, I'm kind of picturing like bubble wrap, basically has flowing water through it and then just adjusting the pressures so that you can control how much pressure is put against the skin. Is there anything around that idea, or is there problems with that? I was just kind of curious.
One of the biggest challenges of the MCP suits is putting the darn things on and off. And the Jessup suit from 2015 was, crudely speaking, a bit like a wetsuit, multiple bonded layers together. And one layer, the outer layer, the compression layer, had pneumatic tubes embedded with it. So it was relatively loose to get on, and then air pressure was supplied to these multiple tubes to provide the pressure, which is a sort of more sophisticated version of the capstan suit, where you just had a gas tube running down your arms and legs and a bladder surrounding your chest that was inflated in the event of needing it.
Indeed, yeah. I was thinking just in terms of thermal management, that'd be interesting. But I should let others ask questions here, so I'll let you go. Thanks.
Okay, and then the last question here is, are there any promising materials in existence or in development that might be the right fit for a Mars MCP suit?
Well, a wide range of materials have been investigated already. And gloves are almost pretty much a solved problem. They've been produced by many different or a number of different organizations, and they all work quite well. And of course, for the full body suit, most of them, they're looking at a variety of weaving techniques. So you need to have a woven suit or a knitted suit. So a knitted suit, everything's sort of linked together by loops. A woven suit, you have multiple interlayered, interwoven fabrics at 90 degrees to each other. People have looked at, this is right at the cutting edge and hasn't been done in practice, at electroactive fibers. So you pass a current through these fibers. You have your suit, when you put it on, it's plugged into the wall like a phone to charge. The suit is relatively flaccid. You get into it, you remove the current, and it'll tighten across your body to a preset tension. I don't, as far as I know, no one has actually tried that, but it's I think an interesting concept. Jessup's idea of having small tubes to provide extra tension as required to facilitate getting in, I think works. But that used conventional materials, not neoprene, but similar to that.
Okay, well, yeah, that's it for the questions now. And thanks again, Jonathan, for giving this talk here.
Yeah, glad to be here.
Okay.